Now let's look at the next two problems. So how do we determine which one grows faster? Uh, Now, do not take for granted to think that these both are exponential, therefore they have this comparable growth rate. Well, you have to follow the rules, and the rule is this: you want to look at the ratio of two. Okay, look at the ratio and then look at the results. Now I'm gonna look at the first one. So you're gonna do e to the x raised to e to the x over 4 to the x. And this is the limit x approaches infinity, right? Now, uh, so even though this is infinity over infinity, please do not try to use L'Hopital's rule because in your notes in class, we discussed one of the similar problem, right? If you apply L'Hopital's rule, no matter how many times, it won't help you reduce the complexity of the problem. So I'm not going to do that. So here's the trick. The trick is to uh, x approaches infinity. So you do this. E over 4 raised to power x, right? Raised to power x. Now, what is e over 4? E is about 2.718. I'm going to just say, hey, 2.7, around 2.7, okay? Just around 2.7. 2.7 divided by 4 is 0.6 something, right? Okay, about 0.68, okay, 0.68. Now, therefore, you're gonna say, hey, this limit is uh, about say 0.68. I'm gonna say about, okay, raised to some x power, and this x is gonna be infinity. So a number, a decimal, if you multiply decimal many times, it's just getting smaller and smaller. So therefore, you know this is approaching 0. Okay, you can plug in a number, say x is say 10 or 20, then you see that it's getting smaller and smaller. So you know this is approaching 0. Again, when this is 0, limit 0, which one is larger so that the ratio is 0? You know this one has to be larger. This one has to be larger. Therefore, I know this guy grows faster than the e to the x. I will rank 4 to the x grows faster than e to the x. Even though they're both exponential, they're both growing faster, pretty fast. 4 to the x is growing much faster. Please note this is different from the previous one that I discussed, like 2x over 3x, right? These time they're both linear, the ratio is going to be 2/3. This is a constant. In this case, we say they're comparable. One doesn't grow significantly than the other, but this 4 to the x grows much faster than the e to the x. Okay, now let's take a look at the very last one. Okay, natural log of 4x and then versus natural log of uh, square of 5x. So again, you want to look at the ratio. So allow me to not to skip the limit symbol, but when you write, you should write your limit. How about I just write it anyway? So infinity over infinity type. Therefore, you're gonna apply the L'Hopital's rule. Okay. So when you apply L'Hopital's rule, the top is 1 over x, right? 1 over 4x, but times the derivative of inner, which is 4. So 4 will cancel, just 1 over x. The bottom will be, keep in mind, this is your, actually you can think of these two, you can move these two to the front, don't you think? You can move 2 to the front, 2 can be moved to the front. So therefore, I just need to say 2 times the derivative of natural log of 5x, which is still 1 over x. And then they can be cancelled. Your answer is 1/2. Therefore, these two actually will be comparable. So no matter how, even though there's a square here, they're still comparable based on our calculation. So you can imagine, say, natural log of 5x raised to, say, 1 million, okay, 1 million. And eventually, if it's 1 million, then if you redo the whole problem, the answer this ratio will be 1 over 1 million, okay, 1 million, and it is still a constant, so we will still call these two comparable. They're growing, the growth rates are comparable. So this is it. Uh, at at the end, let's kind of read through this theorem 4.15, the ranking among those popular, famous functions. So natural log raised to any power, the whole quantity raised to any power, this is growing very slow. You can even look at the graph. They grow like this, very slow. Okay, and so it's always growing less slower than any power function, no matter how small this power is. It's always growing slower than power function. And of course, it is still growing, right? So if you multiply the power function multiplied by another natural log function, it's this guy will grow. This guy will grow faster than just the power function itself. Of course, assuming that they have the same power here. When you compare, you want to make sure that they are comparing the same power here. And this is quite intuitive because this guy will be growing. X to the p plus x is the same as x to the p times x to the s. So this guy will be always growing slower than the power function. So this should not be a surprise. This should not be a surprise here. And then exponential function always outgrows the power function, and you can try one problem and then you see that. So the reason is after a certain number of derivatives, this guy will be approaching constant. But no matter how many times derivative, this guy is always exponential, right? And at the end, this is a superpower function. It grows the fastest among these functions that you've seen.